Hello, everybody. In this video, we're going to start the fifth chapter in the textbook, which is titled with the title "The Bernoulli Equation and Energy Equations." And this is the first chapter that we will cover that deals with fluid dynamics, which is the branch of fluid mechanics that deals with fluids in motion. So this chapter is named Bernoulli and energy equations because one of the main outputs of this chapter is Bernoulli equation, which is a very famous equation that we use to describe fluids in motion. And what we are going to go through here is the introduction to the fluid dynamics, the basics of fluid dynamics, and the basic equations that we use to describe fluid dynamics. So, and as we said before, there are two branches of fluid mechanics: fluid statics and fluid dynamics, and it's very or I think we discussed that in details. What is the difference between fluid mechanics and fluid statics and fluid dynamics, and the nature of the systems is very different in the statics and the dynamics, and so it's very expected that the equations that we use in fluid mechanics would be, or fluid dynamics would be very different from the equations that we use in case of fluid statics. And this is very important thing to notice and to keep in mind. It might not seem that important, but this is something that many people who deal with fluid mechanics kind of forget at some point, that you need to know first what is the system type that you are trying to describe using equations, because sometimes there are dynamic systems that people will by mistake will model using fluid statics. Static systems will be described by dynamic equations and the other way around. So doing this is a very big mistake, because if you do this, you will be describing a system with equations that describe another system, which will definitely give wrong results. So you have to know well the nature of the system that you are dealing with, and what are the proper equations that you need to know to use for this system. So this is a very important point that needs to be referred to. The equations that we're going to use here, if you remember, and this is a very good thing to show this, that in the previous chapter 3, we only used the equation of the pressure at a point in terms of the pressure at another point, which is P2 equals P1 plus rho GH. This is the only equation that we used. And even the equation that 2 points at the same height will have the same pressure is the same equation. You just put H equals to 0. So it's P1 equals P2. So it's the same thing. But here, in case of fluid dynamics, we have two types of equations that we are going to use: the conservation of mass and the conservation of energy equations, which we didn't need to use in case of fluid statics, because there is no transfer of the fluid from a point to another. But in this case, we have fluid transferring from a point to another, so the mass has to be conserved and the energy has to be conserved, and these are the basic rules, or the laws that we are basing our equations on. So this is a very clear difference between the equations that we use in fluid statics and fluid dynamics, which is the type of equations, or the types of equations we are using. So what we're going to do in this chapter is we are going to go through the two types of equations, and we will see how we can write them in a way that fits with the fluid mechanics concepts, or the fluid mechanics parameters, that we can use the parameters of fluid mechanics to put them in, or use them in the equations. And at the end, we will see the famous equations like Bernoulli equation, the continuity equation, and how we can reach the forms of the equations and the simplified forms of these equations. So we will start this chapter with some derivations just to see how we can find the proper shape of the equations that we are going to use. Now uh, the thing that we are going to start with is the conservation of mass. And before we go through the conservation of mass, we have to know how to describe mass for fluid mechanics purposes. Um, but before this, there is one important point I want to highlight here, and this is a very, very important point actually, that the symbols that I'm going to be using in my slides, and again, this is what I use in the slides, and I'll mention in a minute why I'm emphasizing that this is in the slides. I use M for the mass, M dot for mass flow rate, uppercase V for volume, uppercase V dot for volumetric flow rate, uppercase V hat for the specific volume, U for the velocity, and AC A sub C for the cross-sectional area. These are the symbols or the terms that I have been using since I was an undergraduate student. The reason I'm mentioning this here in one full slide is that the symbols that are used by the textbook are different, and for me they are very, very confusing, and that's why I prefer to keep using the symbols that I am used to. The volume has this weird V. I don't know, to be honest, I don't know what these symbols are called. These are, I couldn't find them in the Greek letters or in the symbols in any font that I know of. So I don't know what these symbols are, and even if I know them, um, they're very, very similar to each other, and it's hard if you're writing by hand. It's very hard to differentiate between them, and I find it very confusing to see the difference between this and this, for example, or this and the uppercase V. It's not easy for me to distinguish between them, so I prefer to keep using the symbols that I'm used to make it easy for me, and I think for you as well. And the reason I'm showing the symbols in the textbook and the symbols I'm using is that I'm following everything in the textbook except for the symbols, of course. And for any reason, if you want to check something in the textbook, or if you want to read more in the textbook about a specific topic, or whatever, you will find the symbols different. So I want to make it clear from the beginning that these are the symbols that I'm using, and these are the corresponding symbols in the textbook, so you don't get confused if you compare both. Now for the mass flow rate. So we are going to start with the conservation of mass and then the conservation of energy. And for the conservation of mass, before we go through the equation of the conservation of mass, which is a well-known equation, it's mass in minus mass out equals mass accumulated, of course, with the generation and consumption. This is a very, very, very well-known thing that we covered in the mass balance course before. It's going to be the same conceptual law from the conceptual point of view. It's just how we put it. The equation is different, or substituting each term is going to be a little different, but this is the same concept. Now the terms that we'll have for mass in and mass out have to be put in terms of the system parameters, like the velocity, like the cross-sectional area, like the whatever the parameters that we have in the system. And this is why before we go through the equation, we need to know how we can write or express the mass flow rate in proper terms. So the mass flow rate is, the name is very clear that it is the rate of mass flow, which is how much mass is flowing per unit area. Per unit time, how much mass is transferring per unit time. And of course, this is through a cross-sectional area, because it's a dynamic fluid, so it's traveling from a point to another, so it has to go through a cross-sectional area. And the cross-sectional area that we are interested in is the normal cross-section area, which is the cross-section area perpendicular to the direction of fluid flow. So to make it easy, or make it easy for us to imagine the equations that we are going to use, let's take a case of pipe that has a circular cross-sectional area, and there is a fluid that is flowing inside the pipe, perpendicular to the cross-sectional area. So the cross-sectional area is the circle, and the fluid is flowing. And the reason we use this circular pipe is that this is the most common shape of pipes that we have. What you'll find everywhere, that's used in homes and used in chemical plants and used everywhere. So this is the most common shape of the pipes. So now, having this pipe with this cross-sectional area, we will do the same thing we used to do before, which we discussed before in some details, that the velocities will vary from a point to another. So we will take a small part of the cross-sectional area and we will say that this is DAC, which is the differential cross-sectional area, and there is the velocity UN, which is the normal velocity to this cross-sectional area. And this small, very, very small cross-sectional area, the velocity is uniform. So we can calculate the mass flow rate, or do the mass flow rate, or derive the equation for the mass flow rate on this very small differential area. So if we write the equation, we know that DAC, it's the cross-section area, UN is the velocity, and the fluid has density, which is rho. So the mass flow rate, which is a differential mass flow rate through this differential cross-section area, is going to be expressed, or can be expressed, using this equation. dm has units of mass per unit time. The mass flow rate is the multiplication of the velocity times the cross-sectional area, times the density. So density times the velocity times the differential cross-sectional area will have the units of kilogram per second. So meter square and meter will cancel the meter cube, and we'll have this as kilogram per second. So this is the equation that we can write for the differential mass flow rate. And if we want to get the mass flow rate over the whole cross-sectional area, we can do the integration, meaning that we will integrate dm over the whole cross-section area to get m, and it's going to be rho un dac, the integral of this over the whole cross-section area. So this is the expression that we use for the mass flow rate. Of course, this is it's a good expression to use, but the mathematical form that we have here is not an easy form to use, meaning that it's a differential equation that needs to be integrated, and that this integration will lead to the production of the algebraic equation that can be used directly. But still, the integration thing, the step of the integration might not be an easy step, especially if we have a cross-sectional area that is not uniform, or the integration is not easy to be done. That's why we prefer to use the algebraic equations instead of the differential equations, especially, and this is a good point, or important point to keep in mind here, and about fluid mechanics in general, that for practical purposes, for example, if you are doing the calculations to design a pipeline or something like this, you will not have the luxury to do the integrations and the mathematical work. In the practical applications, it's easier, or it's more favorable to go directly for an algebraic equation that can be substituted in quickly. That's why we can have another form of the equation that is an algebraic form, and it's easier to use. And this is done by using the average velocity, and this is done by taking a look at the velocity profile. If you take a cross section of this pipe, I mean, you slice it in half. This circular pipe, you slice it in half, so it's going to be two identical semi-cylinders, if there's something like this, and this semi-cylinder will have a radius r, and it has this center line, and there is the walls of the inner walls of the pipe. We know from before that the we know that the pipe is stationary pipe and the fluid is moving. So the layer of the fluid that is touching the pipe inside the pipe is going to have the same velocity because of the no slip boundary condition, and the fluid at the center will have the maximum velocity because of the symmetry. It's going to be 0 here and 0 here, and the maximum would be in the center, and it's going to be identical to two halves. So the velocity here is maximum and the velocity here is 0. So we can and we'll go through this in some details later, that we can get an expression for the average velocity. And this is what we always use in our calculations, or I would say 90% of the cases that we use the average velocity. The average is, this is the expression of the average, the mathematical expression of the average. If u is function of a, the velocity is variable with the radius, which is the cross section area. Then the u average is 1 over area times the integration of u dAc. So this is how we can write the average of the velocity. So we can rearrange the equation to be in this form, that u average times AC equals the integral of un dAc. If we go back to the previous slide, you'll find that un dAc is the same thing. The integral of un dAc is going to be the same term. So for cases where the density is constant, which we call the incompressible fluids, meaning that the fluid volume doesn't change with pressure, so the mass is the same, the volume is the same, so the density is the same. So if it has constant density, or it's considered an incompressible fluid, we can get the integral, the density out of the integral, and we will have the integral of un dAc, which is u average AC. So this is a very useful relation that we can use, because in this case we don't need to go through the integrations or do any other mathematical work. You just use the average velocity directly using an algebraic equation. Okay. There is one other thing, which is the volumetric flow rate, which is the mass flow rate divided by the density. Because we know this from before, the mass flow rate equals rho times v dot. It's exactly like mass equals rho times v. So we can write the volumetric flow rate is u average times AC. So this is the or these are the equations that we can use to describe the mass flow rate. Starting next video, we are going to write the equation and see how we can plug this equation in the general, or the big mass balance equation, or the conservation of mass equation. So I'll see you next time, inshallah. Goodbye.